Come along, everyone. We're taking a little trip to outer space. That's right, we're talking orbits. And to start us off, let's first think about what we already know about how an object moves through the air. We're familiar with projectile motion at this point, where if we have an object on flat ground, we shoot it up in the air at some initial velocity, it leaves whatever does the launching, and gravity is going to start pulling it back down to Earth in a parabolic fashion. And this is a really good approximation for how things behave at your ordinary, everyday level. Most things that you can throw or shoot are going to come up and down just like this. However, if you get fast enough or high enough, things start getting a little bit different. And this was thought about far before we even had space travel, back in the 15, 1600s, with a little thought experiment we call Newton's cannonball. Newton, a proponent of shooting stuff really fast apparently, thought, what if we built on our Earth a really tall tower? And we get someone to throw an object off the tower. So at low velocity, our object is going to come out a little bit, and it's going to fall down due to gravity and fall somewhere on the ground. And that's what we expect for a projectile. Even on a tall tower, if you throw an object, gravity is going to bend it down. The speed that you're throwing it at makes it so the forward distance it travels is really, really small compared to the size of the Earth. Thus, the curvature doesn't tend to matter at these low velocities. Now, as you ramp things up, Newton said, hey, well, what if we shoot this thing a little bit faster? So we have like a medium V now. Well, this thing can get fast enough so that, it starts going. It's fast enough that before it starts to fall, it can cover a large distance. So now it's on this part of the Earth, and it starts continuing to go around, but it doesn't have quite enough speed to get to the other side. It falls somewhere. If we're shooting at the North Pole, we get down to the equator, maybe. So the logical extension of this is, how fast do we actually need to go to orbit at the height of this tower? Well, if you get high enough, theoretically, we shoot from our tower here, we go pew, and now what happens is we miss the ground completely, and the cannoneer ends up shooting himself in the back of the head. In other words, we've created orbit. And that's all really an orbit is you're going fast enough that you begin to sort of cheat the notion of what down really means. If we think about this a little bit more carefully, now we're no longer shooting cannons off of a tower, but we're looking at, a satellite or something far above the surface of the Earth. So here's our satellite. You can give it some little fins, why not? We know that the force of gravity due to the Earth on the satellite points directly down towards the Earth's center. So we can draw that force diagram, a little arrow pointing down, and we label it mg for gravity. Now, if I place my satellite up here and let it go, it's going to follow the arrow exactly. What's going to happen is its gravity is just going to pull it down. The satellite will fall like anything else. However, if we kind of replicate Newton's cannonball up here and we give this thing a pretty fast push horizontally, tangent to the circle of the Earth there, what's going to happen is, yes, the Earth is going to pull the satellite down. But because this thing is moving fast enough, it's going to move over to the left as we've drawn it here. So that means a little bit of time later, it will have fallen down. Now my box is here. We've moved over to the right a little bit on top of that, but because we've moved around the curvature of the Earth, the meaning of down has changed. Instead of pointing straight down towards the Earth's center, now, relative to where the satellite is now, the force of gravity points inward, like this. But that tangential velocity is being brought with it, so the velocity is this way now, which lets the satellite, fall down this way towards the center of the Earth while continuing to move tangent to the circle. So now we're over here, almost off the paper. And our definition of down changes yet again. Gravity keeps changing. So all an orbit really is moving with a horizontal velocity fast enough to cover the Earth's curvature, or whatever planet you happen to be orbiting. As you move around that curvature, gravity points to the center of the Earth, which is no longer directly down as we drew it originally. That down vector keeps changing its direction. And if there's no real meaning for down, if you're moving fast enough that down keeps changing for you, you don't fall down. You maintain your elevation, and that is what we call an orbit. So elevation above the Earth is maintained. Stays constant, and that is what we call an orbit. So now that we know how an orbit works, all you're doing is moving fast enough to go around the Earth, changing where gravity is pulling you down towards. We can start to think about how to predict how fast you actually have to go to maintain this orbit, and other aspects of how things move once they are in this gravitational influence. So first of all, we need to rethink gravity. I started off by saying that the force of gravity, Fg, is equal to an object's mass times g, the acceleration due to gravity. And that's a perfectly good approximation for how gravity actually works. This works on everyday scales when you're on the surface of the Earth, which is where like 99.999% of people spend most of their time. However, if we want to, include the full 100% of people, or start thinking about how gravity affects planets and stars and galaxies, we need to kind of zoom out from this approximation here. This is a perfectly good equation most of the time, but it's a little bit nearsighted. It doesn't capture the full extent of what gravity can do. And again, I will show you how this equation relates to the one I'm about to write in a couple of minutes. So here is what we call the universal gravitational equation. This is little g. It works sometimes. This equation, which is the universal gravitation law, now has a big G. This is what we call the universal gravitation constant. We take this mass, little m, so that could be the mass of the object, the mass of the person or the satellite that we drew above, and then you multiply it by big M, the thing that's doing the pulling, the Earth, for example. Then we divide by the distance between their centers of mass, and we square it. So just as a reminder, G is a constant, and you're going to love this, people listening to the video right now. The constant is equal to 6.67 times 10 to the negative 11. There's some units there, but I never remember them. I don't really expect you to either. M is the mass of an object. Call it object 1. Usually it's the smaller object, but in principle, it could be any two objects. And then M is the mass of the second object. Here we're denoting maybe the mass of the planet. But again, this is universal. Any two things with mass exert gravitational forces on each other. Try it between you and an object in your house. See how small the force you exert actually is. And then R is the distance between both masses' center of mass. If you work with a specific set of constants, for example, if you let R equal the radius of the Earth, if you let big M be the mass of the Earth, and you let G, well, G is just a constant, as always is. If you roll all those things together, it turns out that G M of the Earth over R Earth squared is equal to 9.8 meters per second squared. So the equation that we've grown to know and love, F equals mg, is really this more complicated looking equation with a couple of constants plugged in and substituted in for g. This g is just the value of these constants, gm over r squared, when you are at the surface of the Earth. And you can use this to find surface gravity for any other planet. You take the mass of the planet, you look at the radius of that planet, and that will tell you the gravity you would expect to see at the surface. So for reference, Mars is about a third of the Earth gravity. It's like 3.2 meters per second squared. If you use the radius and mass of Mars, on the moon is about a sixth of Earth's gravity, 1.6 meters per second squared. Couple things to think about with this new universal gravitational formula is that g is really small. This 10 to the minus 11 means that this force in the grand scheme of the universe is pretty small potatoes. Gravity doesn't do a whole lot of effort fundamentally. The reason that the Earth feels so strong, the gravity that we feel every day feels so oppressive, for lack of a better word, is that the Earth has a lot of mass. You can get over this 10 to the minus 11 when the mass of the Earth is something like 6 times 10 to the 24 kilograms. If the average person is only about 75 kilograms, that's 7.5 times 10 to the 1. That means the mass of the Earth is essentially a million times another million times stronger than your mass. It's larger than your mass. So that's why gravity feels strong, because the Earth is so massive. But if you were to look at the grand scheme of things, gravity is a weak force compared to things like electricity or whatever's going on in the nucleus. Another thing to think about for this equation is this r squared here. If we're thinking about how forces should scale with distance, that square is really important to consider. So we can consider f scaling like 1 over r squared. This little squiggle here means goes like, or is proportional to. For two given objects, the masses are going to be constant, and g is a constant. So if we're just figuring out how that force is changing as we're moving away from the planet, or the masses are moving apart or closer to each other, we can really just focus on this r here. If we double the distance, well, what's going to happen? R is going to map to twice R. It's 2 times as large. And so if I plug that into the scaling relationship now, I put the 2R in parentheses, and both of those things become squared. We're going to apply the square to each of those symbols independently. So we get 2 squared is 4, and R squared is R squared. And this, if I look at it, is I started with 1 over r squared. I made this transformation, and now we have a fourth of what we started with. So in other words, because of this square relationship, doubling r makes it go down by a fourth. That squared matters. Whatever I do to r, the square is going to happen to the force, and it's going to happen in the opposite way because the r is in the denominator. So this is what we call an inverse square law. It appears a lot in physics. You'll see it again in electrostatics. If you're doing anything with sound intensity, moving away from the source of a sound, you'll see an inverse square law. Really what it happens to do is secretly spherical symmetry. Planets are spherical. Electric charges are spherical, and if a sound is emitting equally in all directions, it will also be spherically symmetry. So we see a lot of r squares when things kind of look like spheres. All right, we've introduced the universal gravitational equation. Now let's look at how we can actually predict how things should move. We want to know how fast do we need to get the cannonball to go around the Earth. So let's figure out how we can do that. Imagine I have something already in orbit. So here is a planet or a sun or something like that, and here is a satellite or a planet orbiting that other thing. So our planet is going to move around this circular orbit here. It's going to have a tangential velocity, v, that it's moving around in this orbit. The planet is a distance r from the other object. And we want to know, how fast do I have to go to orbit at this speed? How fast to orbit at distance r? Well, when analyzing most things in physics with forces, you draw a force diagram. So here's my planet, a little dot. I'm going to draw a force. The force of gravity is going to point directly between the two objects, and the force is going to point towards the other object as an attractive force. So this is my force of gravity. And I'm done. That's the only force acting on the object. That means because we're moving in a circle, the net force is what we call the centripetal force. So here, the force of gravity is equal to the centripetal force that pulls it around in a circle. In other words, this object moves in a circle because gravity is always pulling it in towards the other object. So now we're going to make some substitutions. We're going to take our universal gravitational formula, G big M little m over r squared. And we're going to set that equal to the centripetal force, which has a formula mv squared over r. So a couple neat things to point out here. One, we have a little m on both sides of our equations. That means the mass of the thing doing the orbiting doesn't really matter. The speed is independent of the object's mass, which is good because, once you get the object up there, it doesn't matter how it weighs, though I suppose NASA might care about how heavy it is to actually get that payload up off the Earth. That comes later. But the mass doesn't really matter yet in this equation. So we can cancel out the m's. We can also cancel out an r from each side. So we're going to lose all the r's on the right-hand side. The r squared is going to lose 1 power, and we end up with just a single r in the denominator. So making those cancellations, we get gm over little r equals v squared. And now all I need to do is solve for v. Take the square root of both sides, and we get the relationship that v is equal to the square root of gm over r. So this is what we call orbital speed. If you want to orbit an object at a farther distance, it's easier. So this says that as r increases, the speed you need to maintain your orbit decreases. So Newton's cannonball, still near the surface of the Earth, has to go pretty fast to make that happen. As you get further and further away, the influence from the actual planet is going to decrease, and you're able to move much more gently around the planet than you would you were closer up. So v scales like 1 over root r. This means farther away requires less speed. We also scale v with the square root of m, which means you need to move faster to orbit at the same radius around a heavier object. You would need more speed to orbit the Earth at a certain height than you would to orbit the moon, in other words. So more speed needed to orbit a larger planet, more massive planet, we'll say. It turns out to orbit near the Earth's surface, you need a speed that would essentially get you around in about 90 minutes, which is also about what the International Space Station orbits at. So kind of an aside here, in orbit, what's essentially happening is objects are in constant free fall. We talked about how they are falling, but since down is changing, they just keep falling in a circle. Buzz Lightyear had it right. He was a spaceman after all. He knows that falling or flying is just falling with style. That's all an orbit is. You are in constant free fall. And this is actually the cause of the weightlessness, the low gravity looking effects you see in those videos from the International Space Station. So this is what causes weightlessness. It's not that um, there's less gravity up there. I mean, there is, but if you actually run the calculations, if you look at the G value at on the ISS, Gm mass of the Earth over the r that it orbits at squared, that value only ends up being about 89% of our Earth gravity. So most of the gravity that you have on the Earth's surface is still present on the International Space Station. It's just because that thing is hurling around every 90 minutes, one complete loop around the Earth, they're falling, and they're falling fast. The space station is literally dropping out from under them every split second, and so that causes the weightlessness you expect to see in space. It's not that there is less gravity. It's pretty remarkable how much gravity there actually is up there. So weightlessness is caused by that constant free fall. Last thing to mention in our discussion of orbits are three very important results made back in the 17th century, early 17th century, in the form of Kepler's laws of planetary motion. These kind of give us really guidelines on how objects move. We modeled an orbit up here with a circle. It turns out that from all the observations and all the number crunching that Kepler did, he found that most planets actually move around the sun in what is an elliptical or oval shaped orbit. Earth's actually is pretty circular, by the way. It's really close to being a perfect circle, but it's not quite there yet. Other orbits are going to be more elliptical. So Kepler's law number 1 says orbits are ellipses with one with the larger object, with the sun. He was looking at planetary motion specifically, but these can be applied to anything orbiting anything else. Orbits are ellipses with the sun at one of the foci. So we need to delve a little bit into oval geometry here. If I draw an oval, it's kind of like a stretched out circle. A circle would have a dot right in the center, but we've stretched this thing out. So it turns out the circle literally had two dots laying over top of each other at the center. When you stretch that oval apart, those dots move apart. And depending on how much you stretch it, those dots come apart. So it looks like we're starting to draw like Baymax or Stewie here, but these points right here are just the foci, not eyes. Kepler says the sun would be at one of them. So the sun is located at, say, that focus, and the object moves around this oval path around here. So there are some points in the orbit where it's really close to the sun, and it's further out when it gets to the other side of the sun. So the distance from the sun is not always constant. For the Earth, it's more or less the same. For other planets, you do have really close approaches and you have further aparts. For things like comets, which are very elliptical orbits, you have something where like the comet actually spends most of its time away from the sun and out in deep space, and then when it comes by, it whips around really quickly, which sort of brings us to our second law. This law says that an orbit sweeps out equal areas in equal times. What the heck does that mean? The way I like to think about it is if we go back to our elliptical orbit here, here's our sun. We like to think our planet moving around is attached to the sun by a really long bar or a string or something like that. And it's elastic, so it can stretch and squish as needed so that the planet stays on that track. This line's always connecting the two. Attached to the bottom of this are special paint brushes that sort of paint a surface as they sweep around. So this orbit's going to stretch around the ellipse like this, and it's going to paint as it moves. So if it moves a little bit, now my object is here, it paints out an area like this, right? It's painting the area below. It's sweeping out the orbit. If I'm further away, in the same amount of time, I go from here to there, and I paint out this area enclosed by those two lines. Kepler says the area you sweep out over here, where we have kind of a short base triangle with a wide base triangle with a short height, is an equal area to this triangle over here with a really tall height but a really skinny base. So this one has wide base, short height. Over here we have tiny base, tall height. And if this took, a couple months to happen and this took the same couple months, these areas should be equal. If we think of a triangle, it's a curved triangle, but it essentially follows the rules of 1/2 base height for our triangle area, as this base and height kind of switch places. As the base widens, as the height shrinks, and the base shrinks as the height gets larger. You get equal areas in equal time. This is secretly a statement of conservation. It's a conservation law under here, and it conserves angular momentum. It's a kind of momentum that has to deal with rotating or moving in a circular or elliptical trajectory. So that is the second law. The third law relates the time to go around the orbit, the period of the orbit. It says that the square of the period, the time it takes to go around once, is proportional to the orbit's, here's a $3 word for you, semi-major axis. And the semi-major axis is cubed in this relationship. In other words, we can write t, that's the period squared, is proportional to a, the semi-major axis, cubed. So this t here is the period, that's the time it takes to get around. A is the semi-major axis, it's the size of the orbit. And I'll explain what that means in a second. We draw our ellipse. A circle has a radius, but in a circle, everything is equal from the center. If I find the center of the ellipse, I have this distance here to the short side of the ellipse, which is, we're going to label B. We also have this thing that's analogous to the radius over here that I'm going to call A. That's our semi-major axis. It's along the long side of the ellipse. The semi-major axis is kind of the long half distance of the radius. Semi means half, major means big, so this is the axis that points halfway across the big side of the oval. It's the radius, but not all radii are equal in an ellipse, so we're looking at the biggest one. So the biggest axis of the ellipse, the semi-major axis, is related to the period in this strange way, where the period is squared and the a is cubed. We can kind of play around with that a little bit and show that t is equal to a to the 3/2 power. I just took the square root of both sides to solve for t, and we get this interesting scaling relationship. So you can ask scaling questions here. What happens to the period as I get further away from the sun or the planet or whatever I happen to be orbiting? So we can ask, if you quadruple the semi-major axis, or a much bigger orbit than we were, what happens to the period? Well, we're going to map A to 4A. That's the scaling here. So 4A goes in the parenthesis, and the 3/2 power is going to be applied to everything. So that means I have 4 to the 3/2 and A to the 3/2. I can do the powers in either order, so I'm going to do the square root for it first. Square root of 4 is just 2, so now I have 2 cubed times A to the 3/2, and 2 cubed is a nice clean 8. And I end up with 8 times the thing that I started with. So if I quadruple the semi-major axis, it goes up by a factor of 8. Whatever you do to the semi-major axis, the period is going to change by a factor of that change to the 3/2 power. So that does it for Kepler's 3 laws. We now know how to predict what orbits are going to look like. We know how to predict how fast we need to go to maintain an orbit, and now we know the true form of gravity. No longer are we confined to the surface of the Earth. So that is your intro to orbits.